So MO theory can actually predict some pretty cool physical properties, such as magnetism. So we'll go through a couple of these definitions. So we have ferromagnetic. So this is a material that contains unpaired electrons and is permanently magnetic. So this is what our common magnets are made out of. And by ferro, so that's an older term used for iron. So typically when we're talking about ferromagnetism or ferromagnetic material, most of the stuff that you're going to commonly encounter contains iron. Okay. So, but now we have these other two types of magnetism, paramagnetic and diamagnetic. So paramagnetic is a material that contains unpaired electrons and is only magnetic under an applied magnetic field. So when the field is turned off, the magnetic properties are unimportant. Okay. So again, comparing ferromagnetic and paramagnetic, ferromagnetic means the material is permanently magnetic. So these are, like I said, your refrigerator magnets, right? You can pull that thing off of the refrigerator and hold it in your hand. It's still magnetic, but because you are not magnetic, you don't notice. Okay. That's very different than paramagnetic. And so with paramagnetic, we have to apply some type of magnetic field. And so generally magnetic fields can be created by spinning electrons round and round and round, or spinning a current. So this will also give us the right-hand rule. So you can make an electromagnet by wrapping a bunch of wire, and applying a current through that. So we send electrons through that current, and then the magnetic field will point in that direction of the arrow that I drew. Okay. So if I apply some electromagnetic field to a material and it becomes magnetic, then it's paramagnetic. And as soon as I turn that off, the magnetic properties go away. So diamagnetic is a material that contains no unpaired electrons and is not magnetic at all, no matter what. Okay. So let's look at some things in MO theory and see if it can predict this stuff. Okay. So this is also pretty cool. Another cool way to see how our series of pi and sigma bonds changes throughout the periodic table. So if we start with Li2, so you can see that Li2 would be predicted to exist because, right, it's got 2 bonding electrons and 0 antibonding electrons. So this would be, a single bond between 2 lithium atoms. So it doesn't have any, and so there's my bonding order, right, of 1. So no unpaired electrons, so it is diamagnetic. So Li2 is not magnetic under any conditions. Okay, what about beryllium-2? Well, you can see beryllium-2 has 2 bonding electrons, 2 antibonding electrons, so that's a bond order of 0. So beryllium-2 just doesn't even exist as a compound. So that's another cool prediction that we can make from this. Okay, what about B2, boron-2? Okay, so that's predicted to have a single bond, right, from our bonding order calculation. Okay, so a boron bonded to a boron. But you can see that it's got 2 unpaired electrons, right? So those 2 unpaired electrons would exist as this diradical, like what we described in oxygen, and it is actually paramagnetic. So if we applied a magnetic field to boron, it would be attracted to that magnetic field. Okay, what about C2? So 2 carbon atoms bonded to each other. So you can see that when it's only 2 carbon atoms and nothing else, that's predicted to exist as a bond order of 2, so a double bond. And everything's all paired up, so it's diamagnetic. Same with N2, and we've done N2 a bunch of times. And we note that it's predicted to have a triple bond. Okay, no unpaired electrons, so it is diamagnetic. Aha, but remember oxygen, right? We described oxygen as a diradical, okay? And there they are, those 2 unpaired electrons, and oxygen is also indeed paramagnetic. And this is really fundamentally interesting because, again, 20% of our atmosphere is oxygen. And little did you know that if we applied a strong magnetic field, that oxygen would respond to that. Now, for those of you that are good geologists, you might know that the Earth does have a magnetic field. It's very weak, actually. It's not strong enough to influence the oxygen in our atmosphere. However, if you were to take a strong magnet, like I'm going to draw two, like, let's say we had like a big North Pole and a big South Pole, an electromagnet. So we have like some type of field between those two poles, okay? If I were to pour liquid oxygen down through this gap, it would appear as if it freezes. However, it just becomes stuck between the two magnets, which is really cool. So I meant to attach a video to this, and maybe I'll attach one on the Canvas page, but there's tons of cool videos where you see people pour liquid oxygen out of a dewar in between some magnet like that, and it just sticks. It like defies gravity, which is really cool. Okay. So F2, if we keep going down the line. Oh, and also I forgot to point out, you notice here, this is where the switch happens, right? So we've got sigma 2s, sigma star 2s, and then pi bond, and then sigma bond, okay? And so if we follow along with this here, everything looks good, and then it switches with oxygen. And the reason why it switches is because oxygen is more than half full. So we remember that each nitrogen was a 2p3, but each oxygen is a 2p4. So it's that half-filled orbital that makes this thing switch. And you notice here that F2 follows the same trend as O2, as does neon 2. Okay, so but continuing along, we can see that F2 is predicted to have a single bond, and that's what we would have gotten from the Lewis structure, and no unpaired electrons. So F2 is diamagnetic. And then finally, right, I talked about how helium-2 doesn't exist. Well, we also recognize that neon-2 doesn't exist because, look, we've filled up all of these orbitals. There's the same number of bonding electrons, 6, as antibonding electrons, 6. So again, we can't bond the noble gases. Okay. So, and as the final, very last cool thing that I want to point out about MO diagrams, so we use these routinely to look at spectra and color of molecules. And there's a really, really cool phenomenon on planet Earth that I want to talk about. So I've been speaking ad nauseum about nitrogen and oxygen, right? 80% of our atmosphere is nitrogen. Let's write that down again. 80% of atmosphere is N2, and 20% of our atmosphere is O2. There is a really cool phenomenon at the poles called the auroras. So the aurora borealis in the northern hemisphere, or the northern lights, and the aurora australis at the southern hemisphere, or the southern lights. And did you know that those are actually due to nitrogen and oxygen? And we can actually see that in their MO diagrams. So what ends up happening here is the atmosphere. So here I'll draw Earth. Okay, there's my crude drawing of Earth. We get all kinds of rays from the sun, right? And most of these are light, but a good amount of these are what we call cosmic rays. So these are high energy particles. Okay, they're really, really high energy particles. And they're high enough energy that they can actually promote nitrogen in the top of our atmosphere to go into an excited state. So sometimes we write an excited state. Notice how we wrote that as N2 star. That would be an excited state of nitrogen. So these cosmic rays are striking the very top surface of our planet. Most of these are deflected away from our the magnetic field on the planet. Okay. However, some of them can strike the top of the atmosphere and cause an electron to promote to an excited state, right? So here's my ground state nitrogen. And notice that when a cosmic ray strikes it, it gets promoted, right? One of those electrons unpairs and it gets promoted to an excited state. Well, that nitrogen wants to release some of that excess energy. And so when that electron falls back down to the ground state, it emits light in the process, just like what we learned in our hydrogen spectra. So light is given off. Well, as it turns out, that light is between 650 and 680 nanometers, which is this beautiful deep red color that we can see right here. Okay. Also, another line or another color that's observed, these cosmic rays can also ionize nitrogen. So notice now that's N2 plus. So it removes one electron. So you can see our ground state nitrogen molecule. And then here's N2 plus. We've removed one electron. And not only can it ionize nitrogen, but it can also elevate it to an excited state, right? So you can see there's my missing electron for my N2 plus star, my excited state of nitrogen. And that's a much higher energy state. So when this crashes back down to the ground state, it also emits light, but it emits more energetic light. So this ground state molecule to excited state emits in the red, and this excited state nitrogen ion transition emits more in the blue because it's higher energy. And once again, you can see that right here in this table, this blue-violet, which maybe we can kind of detect right there. And similarly, if we were to draw up another diagram for oxygen, and it can do O2 or even just single oxygen atoms, these cosmic rays are super energetic. Okay. So you can see those are predominantly responsible for making more red and green. So this is just so cool to me, and it actually creates this kind of universally expected thing amongst other Earth-like planets, that we also expect that we would observe auroras on other planets, and not even Earth-like planets, other planets that have rich atmospheres with small molecules such as these. So for example, Jupiter has beautiful auroras on its poles. Okay. So I just think this is very cool to take, to start simple with these molecules, and then we can explain this natural phenomenon, this beautiful natural phenomenon that is the auroras, and many other phenomenons we can describe as well. Okay, folks, that's it for chapter 9. Have a nice Thanksgiving break.